Welcome to HEC Physics. In this video, I'm going to explain some of the key concepts of Level 3 mechanical systems. NCEA Level 3 mechanical systems is made of mainly 4 parts. And in each of these parts, you basically analyze different types of motion. So these 4 parts are, first of all, linear or translational motion, where we analyze motion of objects mostly in straight line. Then secondly, we have circular motion, which is objects movement in circular path. Then next we have rotational motion, where objects are rotating about an axis. And then finally, we have simple harmonic motion. So this is a type of oscillatory motion where the motion is repeated with time. So in this video, I'm going to focus on the linear or translational motion of this standard. So in linear or translational motion, the first concept that we have to understand is and apply as well is momentum. So we'll start with momentum. And you might be familiar with momentum from level 2 physics, because this is a concept that is used in level 2 physics as well. So momentum is associated with object's motion, and it depends on both mass and speed of the object. So the symbol we use to denote momentum in physics is small p, and its unit is the unit of mass, which is kg, and the unit of speed, which is meters per second. And it's defined as momentum p is equals to mass times velocity. So you simply have to take the mass of the object and multiply it with the velocity to get the momentum. Now this is a vector quantity. That's something that you have to keep in mind. So if it's a vector quantity, we often denote it with an arrow, overhead arrow, which means it has both magnitude and direction. So whenever you're analyzing momentum, you have to keep that in mind, that both magnitude and direction of the quantity has to be taken care of in the analysis. And the direction of momentum is same as the direction of velocity, because mass is a scalar quantity. It does not have any direction. So whatever the direction of velocity is, momentum is in the same direction. So something to keep in mind is this is a vector quantity with both magnitude and direction. And this is crucial, especially in level 3 physics, because when we are analyzing momentum, we have to use the fact that it's a vector. Okay, what do we have to do with momentum? Now, something that we have to analyze in level 3 physics is change in momentum. And often it's defined, or often it's called impulse. So impulse is basically change in momentum. And if you have an object which is initial momentum pi, so let's say we have something which has an initial momentum because of its mass and velocity. Its initial momentum is pi, and its final momentum, so something happened and its momentum changed and its final momentum is pf, then the impulse or the change in momentum is delta p, which is equals to always the final minus the initial momentum. And this impulse or change in momentum occurs, so this occurs, so whenever there is a net force, it could be a single force or it could be a combination of two forces, but there has to be a net force acting on the object. Okay, Now this change in momentum over here, delta P, which is remember it's a vector quantity, so you have to keep that in mind when you're calculating this change in momentum. But this change in momentum or the impulse is proportional to the net force acting on it, F, and F is the net force, and it also depends on the amount of time the force acts on the object. So if you apply the same force but for a longer period of time, then the change in momentum will be much bigger. On the other hand, if you apply a large amount of force, then the change in momentum can be bigger as well. So change in momentum depends on the force that is acting on it, the net force that is acting on it, and also time the force was acting on it. And combining this, we can also write the change in momentum delta P equals to force. This is basically the average force. The force can change with time, but this is the average force multiplied by time. So this is known as the impulse relationship. So this relationship is basically the relationship between change in momentum, or sometimes referred to as impulse as well, and it will be measured in kg meters per second. Then this here is the average force measured in newtons, and this here is the time the force acts on, and this will be measured in seconds. Now let's look at an example of application of this impulse relationship. So we are now going to consider an example on how to apply this impulse and force and time relationship. So the example we are going to consider is where we have a ball, and the ball is moving in this direction at 10 meters per second, and the mass of the ball is 0.5 kg. So the ball is coming in, and then it collides with something, let's say a bat or something, and then because of the collision, it changes direction, and now it's moving in this direction. So the mass, it's the same ball, it's still 0.5 kg, but now its velocity has changed both in magnitude, it's now 8 meters per second, and as you can see from the diagram, its direction has changed as well. So overall, the velocity has changed. Okay, so what we have to calculate, we want to calculate the change in momentum, or you can call it impulse as well. Now, because we have the mass and the initial velocity, mass and the final velocity, so we can calculate the change in momentum by using the final momentum minus the initial momentum. And we are using this because based on the information given to us, we can work out what is the initial momentum. It will be mass times initial velocity. And in this case, mass is 0.5. Initial velocity is 10 meters per second. So this is going to be 5 kg meters per second. And I will just draw a little arrow to show that this initial momentum is to the right. Okay. And final momentum is same process, but this time we'll use the same mass and then the final velocity, which is 8. So this turns out to be 4 kg meters per second, and this is going up. I think it's always a good practice to keep track of the direction, because in level 3 physics you have to use the vector properties of these momentum whenever you're doing calculation. So that's why keeping track of direction is extremely important for this type of momentum calculation. Okay, so now let's put the values of PF and PI in this formula over here. So delta P will be equals to 4 kg meters per second, because final is 4 kg meters per second, and I will draw a little arrow going up, and then 5 kg meters per second is the initial velocity going to the right. So as you can see, these two vectors, the two initial and the final momentum, are not in the same direction. They're in different directions. So we have to use vector diagram for the analysis. Okay. So if you remember from level 2, if you are subtracting two vectors, you keep the first vector as it is. And a negative vector going to the right is same as a positive vector going to the left. So if you're subtracting two vectors, you have to flip the minus sign subtraction to addition, and at the same time you have to swap the direction of the vector. So basically we have to add these two vectors, and to add vectors we have to use vector diagram. Okay, so let's put it in a vector diagram. We'll draw the first vector, which is 4 kg meters per second. So we'll draw an arrow going up, maybe length 4 centimeter, and then we have to draw head to tail. So from the head of this first vector, we will draw our second vector, which is 5 meters per second going to the left. So this will be 5 centimeters, slightly longer than the other one. And then the total is always from the start to the finish. So it should be going this way, because this is start and this is finish. Start of the diagram to the end of the diagram. That's your result. So this side over here is our 4 kg meters per second, and this side over here is 5 kg meters per second, and this one is our delta P. So this delta P, using Pythagoras, is going to be square root of 4 square plus 5 square. What are we going to get is 6.4 kg meters per second. So that's our change in momentum. So that gives us the magnitude of the change in momentum. Remember, change in momentum or impulse is also a vector quantity, as you can see from the diagram. The magnitude or the size of this change in momentum is 6.4 kg meters per second, but because it's a vector quantity, we also have to specify the direction. And the way to specify the direction is to specify the angle between this impulse, delta P, and one of the two vectors. Over here, I'm going to specify this angle over here. So we need to work out how much this angle is. And for that, we can see this is our opposite, because it's opposite to the angle. And this is our adjacent. So we know the adjacent and the opposite. So we can use our trigonometry function TOA, because TOA has O and A in it. So using TOA, we can say tan of the angle theta is equals to opposite over adjacent. So that gives us opposite is 5, adjacent is 4. So from this we get theta equals to tan inverse of 5 over 4, and that is equals to, so this turns out to be 51.34 degrees. And I'm going to round it to two significant figure. It depends on how many significant figures we have in the numbers we have used. I think I have two significant figures, so I will keep two significant figures over here. The next thing we are going to calculate over here is what is the so we are going to calculate the average force acting on the ball during the collision if the time or the duration of the collision is, let's say, 1.5 seconds. Okay. So to calculate this, we are going to use the impulse relationship, where we know that change in momentum is equals to force multiplied by time. This is the average force, and we can rearrange it to work out the average force, which will be change in momentum divided by time. And the change in momentum, we have calculated it before. It's over here, 6.4. So we can use 6.4 kg meters per second. and then divided by 1.5 second. So this is 4.267, or rounded to two significant figure, 4.3 newtons. So that's the average force that is acting on the ball if the collision lasted for 1.5 seconds. And what about the direction of the force? The direction of the force should be the same direction as the momentum. So you can see from here the direction of the force, because force is the vector over here, is the same direction as the change in momentum. So if you remember from our calculation earlier, the change in momentum was in this direction over here. So the force will be in the same direction. And it makes sense because if you look at the collision, if the force acting from this bat is in this direction here, then the change in momentum should also be in the exact same direction. So what you need to remember is force and the change in momentum should be always in the same direction, because that force is causing the change in momentum. So we can show this relationship between force, time, and impulse using a graph, which you might have seen in year 12 as well. So if we plot the average force that is acting on the object during the collision on the y-axis and the time on the x-axis, then if the duration of the collision is small, so if the time, this is how long the force was acting on it, so collision time is quite small, then the average force will be quite large. So you can see the height of this graph is quite large, and the area under this graph is the change in momentum. So this thing over here is the change in momentum. So if we can change the collision so that the time of collision is large, that means it's colliding for a large amount of time, so this is how long the collision lasted for, then for the same change in momentum, then this graph will become flatter, because the area under the graph has to stay the same because it's the same change in momentum, delta p. So in that case, you can see the height of this graph is much smaller. So it shows the average force that is acting on the object is much smaller in that case. So for the same change in momentum, the key thing to remember that by increasing the time of collision, we can reduce the force that is acting on the object. So I'm going to end this video over here. If there is any specific question on momentum or impulse that you want me to go over, or any concept that you want me to explain, please let me know in the comments below. In the next video, I'm going to explain some more concepts related to translational motion, such as conservation of momentum, center of mass, etc. So keep an eye on the channel. See you next time.